Alright. Is it even... Here, wait. Can you tilt it so it's actually like on the...
Oh, my bad, yeah. You're the blue.
Mae30a video group 3.
Yeah.
Yep.
Alright. I'm Evan. I'm going to be walking you through the first question.
You're leading the discussion.
I'm leading the discussion. So we are given this beam. We can split it up into these length values, and it's resting on point C and D. And our job for this one, we have point P. We have a force P here on the end, and we're just trying to figure out what force that would be in order to keep this beam in equilibrium, because we have a force here in the center and then on the opposite end at point B. And so we'll do that. We'll essentially just add up the torques on the beam, and we'll do that relative to point C and D on the reaction forces. So I've got an equation with point D here where we take P times 8, and that's because we are 8 meters away from point D. And then we subtract the 20 kilonewton force from it because it's on the opposite end of point D. We multiply it by the 2 meters that it is away from point D, and then we add 10 times 3, which is from the force in the center. And we can use that, set it equal to 0, and solve for P, and that would give us 1.25 kilonewtons. We would do the exact same thing for point C, and then solving for P again, we would get 95 kilonewtons, and so that gives us our effective range of values for point P.
How come you chose to do it at like points C and D, like respectively?
So I chose those because we can eliminate... Dude,
I'm
I'm
sorry.
We do that because those are balancing points and their reaction forces, and by doing it on those points, we essentially eliminate that force in its entirety. You can literally just pretend it doesn't exist, because the torque is force times radius, and the radius is 0 at that point.
So you could do it like at any point, but you chose those because
it eliminates that.
Because that's an unknown.
I want to get rid of it, yeah.
Yeah, I like that.
Pretend it doesn't exist.
Uh-huh.
You want to go to question?
No.
Alright, yeah, we can just...
Thank you.
Okay. My name's Rowan, and I'll be doing question 3. So we have some bent rod that travels along points A through F, and we have a tension force going from A to H on this side and a weight force on F on the other side. And we have reactionary forces on points D and C, but D doesn't exert any axial thrust, so we can ignore the reaction force in the X direction for D. So let's see. I chose point C to be the moment point because it has 3 different reaction forces, so choosing that point would eliminate the most forces that you didn't have to think about. So we put that equal to 0, and we have our 3 different moments we want to look at. We want the moment from H to C for the tension, the moment about DC for the D vectors, and DF for the weight. So you get your 3 vectors with their respective X, Y, and Z components for the moment, and you do the sum of the moments, and you can figure out the tension and the D's from that. And then after that, you can just set the sum of the forces in the Y and Z direction to find the components for C after that.
So in theory, we could have still done the moment about D and gotten the same answer, but it would just be more...
I don't think it'd be too much harder, but yeah, you could do it around D. That would also work.
Do you know why there's an X component for C but not for D? Or
yeah, so in the problem it states there's no axial thrust, and the axis we're looking at is CD.
Oh,
so there'd be
okay. So just a given.
But C still has the X component, yeah.
But it turned out to be 0, right? I think.
Yeah, because there's no other X component of force in the system to counterbalance it.
Because I think if I was going about this problem, I don't even know if I'd include CX in the first place, knowing that there's no forces that are going to affect it. But I guess it's smart to include it just in case, because you don't know that.
Well, I think if you didn't draw it out, you wouldn't know there's no X force. But yeah, you don't have to include it anywhere in this problem.
But if they didn't specify that there couldn't be like a D of X, we would have had to...
Oh, I think they would have still canceled that, or maybe not.
Oh, okay, yeah, I get you.
But yeah, it doesn't really matter anyways.
But couldn't they still have a magnitude of some kind?
Yeah, they would. Yeah. I guess you could solve it then.
Okay.
How did you know that the moment about C was 0? Like, was that given, or...?
Well, that's what we're assuming when you do the sum of the moments, because, I mean, it's an equilibrium. Yeah. It's an I mean, I guess you can assume it's an equilibrium, so you could set the moment to 0.
Okay, that makes sense. Yeah.
All right.
Thank you.
Thank you.
I'm Thomas Brandt. I'm going to explain questions 3 through 5.
I'm realizing we did our numbering different. Like they did. Yeah.
So I technically on grade scope, I think this is number 2.
Yeah. So Thomas and I numbered them based on what number they were on grade scope, and then they were doing
on McGraw Hill.
Yeah, McGraw on McGraw Hill.
So the first part, we just need to do a free body diagram. That's pretty straightforward. P is our applied force, I think, and then A has an A of Y and an A of X, and then this one's a little tricky, but so this is like basically like a wheel or a roller or whatever on like this ledge here, I guess, and our E force here is just normal to that ledge, and then we're given this angle value, that's our alpha. So for B, or number 4, or number 2, B, this we'll basically make a net X force equation, net Y force equation, net moment about E. And basically what we're trying to do here is we're making a system of equations, so basically we can plug in for different variables to each other and eventually get a numerical answer. In this case, I plugged some stuff into each other. You know, I solved for E first. You could probably do it another way too, and it would still work out. Using that E value, I then plugged it into to find A of X, A of Y. And for this question, we also need to find the magnitude. So that would just be the Pythagorean theorem of the AX and AY. That'll give us that. And then there's also, I forget what it asks exactly. We did need this angle value, which we use inverse tangent, and then we'll use the opposite over adjacent.
What angle value is that?
I'm trying to remember.
Oh, okay. Yeah, I don't remember what it asked.
It's
the angle of combined force of A. It wanted you to put A into one vector.
Yeah. So that should give you around 57.98, depending on your numbers. And then for C, or question 5, you do the exact same thing over again, except they give you a different alpha, in this case 45 degrees. I didn't have to write out all the net equations because I already have like these simplified versions of them, so the equations don't change. The only thing that's changing is your angle measure. So plug in with the new angles and you should get your answers pretty quick. This one, it gave you like 3.514 times 10 to the negative 7, or like a similar
very small
magnitude.
Numbers.
Very, very small numbers, which are approximately 0. So for this, we can assume there's just 0. And the software also takes that. I'm so sorry.
Sorry, my bad. Anybody have any questions?
It's pretty straightforward, yeah.
Good job. All right, so I'm Andrew. This is going to be, oh my goodness, might have to move this back. Thank you. This is going to be number 15 on the McGraw Hill, the way you number it. So here we have a system that is free to rotate about the y-axis, and it's not very clear in this drawing, apologies, but it's like 2 bars coming off in this direction, and it's connected to this mechanism right here. So the whole system is free to rotate about the y-axis, but it's locked in the x and z axes. So that's going to be a key component to when we're solving it. So the first thing I went ahead and did is found the angles that these tensions are at. So these tensions right here and right here. Pretty simple geometry right there, just using inverse tangent. And then we can go ahead and start to create our moment equation. But it's important to note that your total moment is not going to be equal to 0, contrast to a lot of these other problems where it was given that it was 0. And the reason that is, the only place we know is 0 is about the y-axis, because it's free to rotate about the y-axis. But in the x and z axes, it's going to be It could be something else because it's not free to rotate, so there's going to be a force applied in that direction. So we can still go ahead and develop our moment equation using the cross products of this is R and then F, and then I just have an example just for the weight. I didn't want to write out every single one. So just for the weight, you can see this is a cross of the R and the F. So the weight is only affecting in the J direction, and then this is the R vector. So it's this vector going from here. So then ideally you would do this for every force applied about A. And notice that we don't have to do it for the AZ and AX components as mentioned before because we're doing the moment about that point. Those components are going to have zero contribution to the moment. So then we're just going to have our TD, TF, and our weight components that are acting on the moment. So you would have two more matrices. I didn't write them just because I didn't want to. But so you have your weight and then two more matrices, and then once you go the cross products, this is what you're going to get. Oh, I think I need to add a little plus sign here. These are all added together.
Oh, yeah.
So these three vectors are going to be all added together. So you have your I's, J's, and K components. And then you have a system of equations. But I think what I did at first when I was solving this is setting all those equal to 0, which is what we've done in the past, which is not going to work. So you can only set your Y component equal to 0, which I've done right here using the Fy equation. Sorry, that's the Fy. If you set your delta My, this is your delta My. You can go ahead and write that. Oh, this is 2. If you can read that. So that's going to be your delta M. And that's the only one that we can set to 0 because it's fixed about the other axes. So since it's free to rotate, that's the only one that's going to have a 0 moment. And we can get a relationship then between TF and TD, which we can then go and plug in into the delta Fy equation. And you do a similar process to solve for all the others. I didn't write them all out. So you'd have 3 delta M 3 moment equations and 3 force equations, and then you just go ahead and plug and chug from there. But yeah, any questions?
So that was a good explanation. So for these, this is the unit or direction vector of the
Yes,
magnitude
of the tension.
force.
Yeah.
Okay.
Yeah. So that's why they're all like decimals.
Okay.
Yeah. So this R value doesn't need to be a unit vector, but this should be a unit vector. But this is just a unit vector with an applied force, so this is the weight in this case.
When you multiply, we're allowed to just like for example, put like a T up there to multiply.
Yes. So what I did in the other ones, like you could do this one is do this as -1, and then do the W out front.
Yeah.
But yeah, so yeah, you can effectively pull out like that. So that's where these TFs and TDs are coming from. But yeah.
So it doesn't matter that you don't use delta M, X, and Z, right?
So I think
already
the
gives you
key
the
is
variables?
you can't set those equal to 0. You're still going to end up using them in the final answer. I'm going to set up my delta MX, which would be these 3 values, and then my delta MZ. Because we don't know that those are going to be equal to 0. I think delta MZ will end up being 0 just by coincidence, just because of how the tensions are set up. But your delta MX is not going to be equal to 0, and that's just because of how this configuration is set up, where it's free to rotate about the y-axis, which is going to remove that moment, but it's not free to rotate about the x or z-axis, which is going to then have a moment, or possible moment.
Do you remember what you set your delta M and X and Z to? Or is it just
So you don't know what they're going to set them equal to, and you end up just having a system of equations and plugging in and going from there, if that makes sense. Yeah. You can only set the y equal to 0. But then you start solving for variables, and it solves pretty quick.
Okay.
So I would go about first do the delta my, which you know is equal to 0. Then you get a relationship between TF, TD. Then plug that into delta Fy. Then plug for delta Fx and Fz. And then you can go ahead and solve for Mx and Mz.
So it asks for delta MX and MZ.
It does ask for the
You don't
moments,
need to use it to solve for anything, just
Correct.
Okay.
Yes.
Yeah.
Yeah.
I see.
Yeah. Because you'll be able to figure out all the variables, I think, without Mx and Mz.
Yeah, that was my question.
Yeah.
Okay.
Yeah.
That makes sense.
Yeah. Thank you for that question.
Nice. Thank you.
All right. That concludes our video. Thank you for watching. Evan, would you like to come back for the final goodbye?
Yeah.
I'm sorry, Case.
Thank you.